Okay, today we're on page 309, topic 5.7, where it says to simplify as much as possible for problems 1 through 12. And see that little note up there? There is no class Friday, April 12th. There's an academic meet for high schoolers on campus. So they're going to use all the classrooms. So we were told we wouldn't have any place to have class. And we could either cancel class or have you all watch a video. And I decided to cancel class. So you could, it isn't like we're not having class. What I'm doing is I'm giving you that class period to get caught up with your work. Because if we had class on Friday, we would finish chapter 5 on Friday and be taking a practice test next Monday. So you probably need some time to get caught up. So that means on Monday, we'll do topic 5.8. And then on Wednesday, we'll do the practice test. And then, is it next Friday? Is Good Friday? We don't have class then either, do we? So the test will be the following Monday. So you've got a couple of weeks here with 2 days of math to help you get caught up if you're running a little behind. But there's no class on Friday. So if you come in here, it'll be a room full of high schoolers doing academic competitions. And did you notice where it says simplify these? I've put down a little chart of all those perfect square numbers. And the reason I have that chart here, I mean, you could put it on a piece of paper and just carry it with you, just like this prime number chart, is because when it says to simplify the square root of 72, I make this little tree and I factor 72 into 2 and 36. Now, does anyone, now you can probably see why I picked 2, because 2 goes into 72 easily, but there's another reason I like 2, because it's 2 times 36. And why do I like 36? Because it's on my chart there. You see that? So what I'm really doing is I'm taking these problems, numbers 1 through 12 on page 309 in topic 5.7, and I'm building a factor tree so I can get it to the place to where I have a perfect square times something. Then I can simplify, like what's the square root of 36? 6. And what's the square root of 2? There isn't one, so you just leave that as the square root of 2. So your answer is 6 times the square root of 2. Now, I need to ask you a question. Does the square root of 72 equal 6 times the square root of 2? Does that look like that makes sense in your little heart of hearts? No, it doesn't. So working with radicals, you understand you're going to get answers that don't quite feel right. And just deal with it and recognize that you've done the work right. So, and if you want to check it, just take 6 and square it, 36. And so 6 is the square root of 36. Then 36 times 2 is 72, so you can work back the other way. And sometimes working back to check it also helps your head, it helps you wrap your mind around this stuff to the point to where if you've got your mind wrapped around it thoroughly enough, your heart starts to give in and say, okay, I'll accept that. Problem number 4 says the square root of 175, and can you see, as soon as I see 175, I'm going 25. There's my magic number, 25. How many 25s in 175? Well, there's 4 25s in 100, right? And 3 25s in 75, so that would make 7. So I put the square root of 125 times the square root of 7. And then what happens to the square root of 25? it becomes 5 times the square root of 7. So what does this equal? 5 times the square root of 7. Isn't that cool? Now, I did it another way, just to show you. Say, what if I don't see those perfect squares in there? Don't worry about it. If I said, hey, 175, I can divide it by 5, then I get 5 times 35. Then 35 becomes 5 times 7. See that? So now what I have here is 5 times 5 times 7. But what's 5 times 5? Remember, all of this is under a radical. So 5 times 5 is 25. So can you see how I can cross that out and put 5 out here and leave the radical 7 inside? So if I don't see the perfect square number when I'm factoring, building my tree, I can just build a tree like I used to build them and take them all the way down to prime numbers. And then anytime I have 2 prime numbers, those 2 prime numbers together will produce a perfect square. Everybody follow that? Number 6, 162, 2 and 81. All right, so I've got the square root of 2 times what? 9. Go. How'd you know that? The chart. See, there's the square root of 81 is 9. So make a chart. So that's 9 times the square root of 2. Number 8. I'm glad I have my prime number chart handy, because 191 is on my prime number chart. So what does that tell you? You can't simplify it. Well, why do they tell me, oh, simplify as much as possible? So he gives you one you can't simplify, which always bothers me. Why does a math book give me a problem to do that I can't? They say, here's the problem, work it, but you can't work it. Well, then why'd you give it to me to work it? But number 8 can't be factored, so can't be simplified. So keep your prime number chart handy in case you run into one of those. Number 10, what happens with 486? Now see, I didn't see anything when I just looked at it, so I go, well, I know I can divide by 2, and that's 2 and 243, and I know that I can divide by 3, so that's 2 and 3 and 81. 81. See what happens? I work it down far enough, and I'm going, I found one of those perfect squares. So what's 2 times 3? 6. What's the square root of 8? Remember, this is all under a square root sign. What's the square root of 81? 9. So the answer is 9 times the square root of 6. Why did I put a question mark by that? Oh, does the square root of 486 look like 9 times the square root of 6? I mean, it just doesn't. Not even to me. I look at it and say, I don't think so. So watch what you can do. Go 486 with your calculator, just to put your mind at ease, and hit the square root button, and you get 22.045. I'm going, that doesn't look like, well, wait a minute, 22. If I hit 6 and hit the square root button, I get 2.449, and take that times 9, and I get 22.04. You follow? I can take my calculator and mess with it a little bit if my mind is struggling with whether or not I'm willing to accept that answer. Wouldn't you think that doing math correctly would just make sense to us? Being how that God created us in His image and likeness, and He created the world of math. Wouldn't it just make sense to you that pure, correct math would just be obvious? And here's what I say. It probably was in the Garden of Eden before Adam and Eve messed things up. And when they messed us up morally, they messed us up mathematically. So just deal with it. Realize that my depravity, maybe that's why we get upset about making a mistake in math, because it shows my depravity. Well, let's face it, we're depraved. Number 12, 5,000. Now, see, I don't have it written up here on my list, but if my list went far enough, I would have 1,000. What would I have? What? $2,500? Yeah. 50 is the square root of 2,500. So if I know that, I can just go, hey, this becomes the square root of 2,500 times 2. So see what happens? Then it becomes 50 times the square root of 2. But again, if you don't see it, then you say, well, I can divide by 5, and I get 5 and 1,000, and then 1,000 would be 10 and 100, and 100 would be 10 and 10. So see, there's where I've got a 10 and 10 would give me one of those perfect squares, one of those numbers I could take the square root of, but so does 5 and 5. So the square root of 25 is 5, the square root of 100 is 10, 5 times 10 is 50, so there's where I get my 50 another way. You follow what's happening when you start, actually when you start building the tree to simplify these things, you'll start to see, if you've got your list of perfect squares beside you to look at, you'll start to see what's happening. All right, numbers, so now we know how to simplify. Now let's learn how to do what? Rationalize the denominator. Do what? I haven't met very many people who like this. So just deal with it. Because it's using fractions. Maybe that's part of it. Number 14 says 6 over the square root of 5. And you might say, what's wrong with that? And to a mathematician, that's like wearing your shoes on the wrong feet. It doesn't look right. It has to be fixed. And in other words, we don't want irrational numbers for denominators. That's why it says rationalize the denominator. We want the denominator to be a rational number. So watch how we do that. Here's the square root of 5. So I take it times the square root of 5. But if I do that to the bottom of a fraction, I have to also do it to the top of the fraction. Does everyone follow that thinking? Like if I come over here and I take a fraction and I say 2/3. If I take this times 3, then I take this times 3, and it equals 6/9. You follow what's going on? 6/9 is equal to 2/3. So over here, I'm using radical 5 and radical 5. So what's radical 5 times radical 5? Radical 25. What's the square root of 25? 5. Everybody follow that? So what happens to the numerator? Well, what's 6 times the square root of 5? I can't mix rational and irrational, so I just leave it as 6 times the square root of 5. So there's your answer. 6 times the square root of 5 over 5. Now watch what I just said. Problems 13 through 18 say rationalize each denominator. So here's my original fraction, and here's my new fraction. And is this fair to say my new fraction looks more complicated than my original fraction? And it usually will, because I'm rationalizing the denominator. But when I look at this, I get a smiley face because it just looks beautiful. When I look at this, no, that makes me frown, because I don't like irrational numbers in the denominator. Number 16, radical 3 over radical 7. It's a negative, and they put a negative in front of it, so keep track of that. So I take top and bottom times the square root of 7, and then what's the square root of 7 times the square root of 7? The square root of 49. What's the square root of 49? 7. So I've rationalized the denominator. Now what's my new numerator? Now, since both of these are radicals, I can multiply them. Radical 3 times radical 7 is radical 21, and then put the minus out in front of it. And there's your answer. Negative radical 21 over 7. And some of you, I can tell, because you don't like fractions, you're tempted to cancel out the 7 and change the 21 to a 3. But you can't do that. And why can you not do that? Because 21 is an irrational number. It's under a radical, and 7 isn't. So you can't mix, you can't operate with a number inside and outside the radical. You operate with numbers under the radical sign, you operate with numbers outside, but you don't mix them together. Number 18, 3 over the square root of 27. So I just take the top and bottom times the square root of 27, and I get 27 underneath. And then I get 27 on top times 3. But can you make a factor tree for radical 27? 9 and 3. So that becomes 3 times 3 times the square root of 3, which is 9 times the square root of 3, but it's over 27. So now I've got rational numbers out here and down here. I can simplify those. So that becomes the square root of 3 over 9 into 27. Maybe come down here. 27 is 9 times 3. So I cancel out the 9s, and I'm left with the square root of 3 over 3. And that just looks like a work of art. Number 20. Simplify each expression. And what they have is a great big square root sign with all of this stuff underneath. So the first thing you do to simplify it is make 2 square root signs. One for the top and one for the bottom. What's the square root of 16? Look at your chart.
4.
So I put 4, and on top leave the square root of 7, and that's the answer. I'm done with it. I just simplified it. Now, if I would have had an irrational number for a denominator, to simplify also includes rationalizing the denominators. Let's do number 22. It'll work out like that. So here's 25 over 11 under a square root sign. And I go the square root of 25 over the square root of 11. Then I take, 25 becomes, the square root of 25 is 5 over the square root of 11. Then I take the top and bottom times the square root of 11. And I end up with 5 times the square root of 11 over 11. Everybody see how I get that answer? What did I do that's making somebody nervous? Nothing? Well, good. Let's do another one. 24. Radical 18 over radical 25. I just make it radical 18 over 25. But 25, the square root of 25 is 5. And 18 becomes what? 9 times 2. So the square root of 9 times the square root of 2 would be 3 times the square root of 2 over 5. Everybody follow that? $26. Why is this one so messy? The square root of 24 over the square root of 75. Now I think the textbook shows you that you can do something with these things to keep from using such big numbers. But in my mind, one process works all the time. So the first thing is, let's just make the two separate square roots. Then, this becomes, radical 75 becomes the square root of 25 times the square root of 3. So maybe that would help to do that. So now my denominator is 5 times the square root of 3. And my numerator, 24, 4 and 6, is 2 times the square root of 6. Everybody see where I get that? So now, the only thing in the denominator that's messing me up is this square root of 3. So I take the top and the bottom times the square root of 3, and I get 2 times the square root of 18 over 5 times 3. Because the square root of 3 times the square root of 3 is the square root of 9, and the square root of 9 equals 3. So I guess I could come up here and say, so now I have, come out here and write it, 2 times the square root of 18 over 15, if you're inclined to put them together. Then you say, yeah, but I can take 18 and make it 9 times the square root of 3. So that would be 3. So now I end up with 6 times the square root of 3. Not 3, 2. 2 times 9 is 18. 6 times the square root of 2 over 15. But what can I do with 6 and 15? 3 and 2. And 3 and 5. And the 3's cancel. So the answer is 2 times the square root of 2 over 5. And I don't know who taught me to do this, but they said, so don't be so quick to put those together. Just leave them as a sequence of 5 times 3. Then when you factor on top, you'll see things that you can cancel. Like you'll see those 3's that cancel out, so you don't end up doing more mental math than you need to. But if you do all that mental math, you'll eventually, if you put them together, you'll eventually have to simplify them. So you'll get there eventually. It just takes a little longer. So someone taught me, said, so when you're working these things, don't be in a hurry to put them together. Just leave it as 5.3, 5.3. It's like we learn to express large numbers as the product of primes. And it's a good technique in terms of helping you work the problem. So what are we doing now? 28 through 50? Perform the indicated operation. Indicated operation. What's the operation for 28? See that little dot in there? What does that mean?
Multiply.
Multiply. So since I have the 7's under a radical, the 8's under a radical, I just go 7 times 8 is 56. But 56 is the same as what? 4 and 14? Right? So I can take the square root of 4 So the answer is 2 times the square root of 14. Now, to show you what I was talking about before, here's the square root of 7 times the square root of, let's take 8 and break it down, the square root of 4 times the square root of 2. Everybody see what I'm doing there? To make 8, the square root of 4 times the square root of 2. Then what happens? What's the square root of 4? 2. What's radical 7 times radical 2? Radical 14. See how you can save yourself some work? Number 30. Either way, you'll get the correct answer if you don't make a mistake in computation. So just find a preferred way of doing it and go after it. Number 30, radical 10 times radical 5. See, that's just radical 50. But radical 10 is radical 5 times radical 2. And then times radical 5. So what's radical 5 times radical 5? Radical 25, which equals 5. So the answer is 5 times the square root of 2. Number 32. Radical 22 over radical 2. Can everybody see that 22 can be divided by 2? So that just becomes radical 11. I mean, you can put it over 1 if you want, but it's still just radical 11. Number 34, radical 10 over radical 490. Yeah, but watch. See, again, that's radical 49 times radical 10. And so that means the radical 10s can cancel, and I'm left with 1 over, what's the square root of 49? 7. So there's my answer, 1/7. 36, factor radical 18, radical 9 times radical 2, factor radical 12, radical 4 times radical 3, and I'm left with 9 becomes 3, 4 becomes 2, so I'm left with 3, put it up here, 3 radical 2 over 2 radical 3. And what's wrong with that answer? Oh, why is that hurting me so much? Because of that radical 3. So I take the top and the bottom. I'll just change colors here. Times radical 3 times radical 3. And I end up, because I'm rationalizing the denominator, I end up with 3 times the square root of 6 over 6. Square root of 3 times the square root of 3 is the square root of 9. Square root of 9 is 3 times 2 is 6. But I can reduce that down. That would equal what? 6 is 3 times 2. So that equals the square root of 6 over 2. Why is that writing so small? I don't know. Let's pick a bigger one, see what happens. Number 38. Perform the indicated operation and simplify. And what's the operation here? Subtract. Subtract. So I take 32 and make it 16 and 2, and that becomes 4 radical 2. Does everyone see how I took radical 32 and turned it into 4 radical 2? Does everyone see how I got that? Then, here's my minus sign. Then I take the square root of 8 and turn it into 2 times the square root of 2. Does everyone see how I did that? If you don't, then just say, how did you do that? And see, I'll take the radical 8 and make a little tree up here and go radical 4. 8 is 4 times 2. So I have the square root of 4, which is 2. So that gives me my 2 radical 2. So now watch what I have here. I'm going to change colors on this one. I have 4 of these minus 2 of these. What would that give me for an answer? 2 of those. You almost treat radicals like you would variables. So 4 radical 2's minus 2 radical 2's would give me 2 radical 2's. So there's my answer. So I have to simplify the radical and then do the, what are these numbers? Addition or subtraction? Some are addition, some are subtraction, and some are addition and subtraction under a radical. We'll get to some of those. Any questions about 38 before I move on? Did I do something that's making somebody nervous? No? Number 40, radical 24 becomes radical 4 times radical 6. Which is 2 radical 6. And radical 150 becomes 25, because I know that's my magic number, times 6. Whoa, now it's too big. What's going on here? Goes from too small to too large. So that becomes 5 radical 6. So now I have 2 of these minus 5 of these would give me negative 3 of these. Everybody see what's happening? Do 38 and 40 make sense? Do you have a question about 38 or 40? Am I moving too fast? Am I giving you a headache? Radicals will do that to you. They'll just give you a headache. So you might have to go back and look at the video again later to just see what's happening. So now we're ready for a new kind of problem, number 42. See, we've got this huge, big radical sign. And this stuff underneath. What's 5 squared? 25. What's 12 squared? 144. What happens if you add them together? You get 169. Everybody follow? We're working under the radical, so we can do all this stuff. But it's all under a radical sign. Except, look at your radical chart. What's the square root of 169?
13.
So, all of this equals 13. That's your answer. Now, that's really going to mess with your head. Number 44. What's 25 squared? Remember, it's all under this big radical sign. What's 25 squared? You don't know. Okay, get your calculator. 25 times 25, 625. There you go. What's 24 squared? 576. What's 625? I'm going to need my calculator for that one. Minus 576 equals 49. What's the square root of 49? So all of that equals 7. What do you think? Are we having fun yet? Okay. 46. Now I put a 1 out here just so you would know there was a 1 there. There's 1 of these plus 11 of these minus 3 of these. And they're all the same kind, radical 3's. So what's 1 plus 11 minus 3? 9 radical 3's. Okay? $48. Whoops. See, I have 28, 7, and 175. And they want me to subtract them. Well, here's the way you think about it. Apparently, all 3 of these have something in common. Yeah, they do. This is 4 times 7. There's 7. So I must need a 7 over here. 7 times something. What would that be? Oh, 25. See what's happened? I'm looking for this stuff, so I'm saying, so there we go. So now I have 3 times 2 times the square root of 7. That's 6 times the square root of 7. See, this 4 became 2, and this 2 times this 3 becomes 6. Minus 6 radical 7, and then this is 5. And 5 times 2 becomes 10, minus 10 radical 7. So I have 6 radical 7, minus 6 radical 7, minus 10 radical 7. And so that gives me an answer of negative 10 radical 7. Now, what did I do here that's hurting somebody's eyes? You see, when they give me 3 of these things and they tell me to add them, I'm going to look, or add or subtract, I'm going to look for something that's going to be, so I can get them to be the same kind. Sometimes that won't happen, and sometimes you'll just have to have an answer with 2 parts, with 2 irrational parts to it. Maybe we'll see one of those a little bit later. Number 50. 27 is what? 9 times 3. 12 is what? 4 times 3. I'm looking for a 3. 48 is what? 16 times 3. So I end up with negative 15 times 3. Does everyone see how I got negative 15? What's the square root of 9? 3. What's 3 times negative 5? Negative 15. What's the square root of 4? Remember, these are all square roots here. 2. So I have 2 times the square root of 3. What's the square root of 16? 4. What's 4 times negative 5? Negative 20. So I have negative 15 plus 2 minus 20 of these negative 3's. And that ends up being negative 33 times the square root of 3. Number 52. Oh, finally, we get to some story problems. What does 52 say? The hypotenuse of a right triangle is 10 inches long. So I draw a triangle. I make it a right triangle with this little square in the corner, and this is the hypotenuse. That's 10 inches long. Okay? I'm just going from all these words to mathematics because it's easier to work it. One side is 7 inches long, so I call this side 7. Is the other side longer or shorter than 7? I don't know, so I call the other side x. And thanks to Mr. Pythagoras, do you know him? No. Do you know his theorem? This is so cool that he figured this out years ago. He must have been so excited when he found this. In a right triangle, A, B, and C. C squared equals A squared plus B squared. Did you learn that someplace in school? To me, that is so powerful. Let's just draw one out here. See if we can make one of these. No, maybe that one's not going to work. Let me try to move over here and make it a little bigger. 1, 2, 3, 4. 1, 2, 3. So this side is 3. This side is 4. So what's this side going to be? Oh, change to red here. Let's go to red. Make this out here. One, 2, 3, 4. Let's erase that piece. 1, 2, 3, 4. And 1, 2, 3. 4 squared is 16. 3 squared is 9. And if you took a ruler and measured this would be 5. 1, 2, 3, 4, 5. And 5 squared is 25. What's 16 plus 9? 25. So 5 squared equals 3 squared plus 4 squared. And when Pythagoras saw this, he says, does this work every time? And he started making a bunch of right triangles. And sure enough. And from that day on, everybody had figured out how to make a square corner for a garden or for a building or whatever. Because all you have to do is just go 3 feet by 4 feet by 5 feet, and you have a perfectly square corner right here. That's a right triangle. Or if you're making a big one, 30 feet by 40 feet by 50 feet, and you've got a perfectly square corner. So that's where Pythagoras' theorem became so popular. So now what I do is I use the Pythagorean theorem, and I'm going, okay, so 10 squared will be 7 squared plus x squared. So that's 100 equals 49 plus x squared. So minus 49, 51 equals x squared. So I get my calculator out and I go 51 and hit my square root button. And that means x is approximately 7.14. What was the question they asked? Is the other side longer or shorter than 7 inches? And what would you say?
Longer.
Longer, because it's 7.14. So it's longer than 7 inches. So you can't work this problem without having the Pythagorean theorem. So what do you think? Is there going to be a question on the test at the end of this chapter that's going to require you to use the Pythagorean theorem? So should you have it written down in your notes somewhere? If you don't have it in your mind, just write it down in your notes and bring it with you. And draw a picture that says c squared equals a squared plus b squared. You don't even have to remember who thought it up. Just draw a little picture and bring the formula with you. Number 54. Now, does everyone see what I have written here coming from the words on page 310? The time t, I'm going to change the blue again because I just like this blue stuff. The time t in seconds that it takes an object dropped from a certain distance to hit the ground is t equals d divided by 5. See where that formula is there? So then it says on 54, find the time, that would be t, when, where'd it go? Find the time when an object is dropped from a height, that's the distance, of 160. So d is 160. So I come over here and I just put t equals the square root of 160 over 5. What's 160 over 5? 32. So t is the square root of 32. What can I do with 32? 16 times 2. So that equals 4 times the square root of 2. Is that what they want to know? And write the answer in simplified form. So there it is. 4 times the square root of 2 seconds. Does anyone know about how many seconds that would be? Take your calculator, hit 2, hit the square root button. It says 1.4142135. These are irrational numbers. And then take that times 4, and that's about 5.657 seconds. Because generally we don't walk around thinking, you say, what's 4 radical 2 seconds? See, we don't think in radicals. So if you're trying to get a real fix on it, you go take the square root of 2, approximate it, take it times 4, and it's about 5.5 seconds. 160 meters. A meter is a little bit more than a yard, isn't it? So you're 160 yards up in the air. Take a football field, turn it on end, stand at the top of the football field, and have a discussion with your friend. If we step off the end of the football field, how long will it take us to fall to the ground? 1001, 1002, 1003, 1004, 1005, splat. So if you ever decide to go skydiving, you need to know something about how many seconds it's going to take you to hit the ground. And you better know something about how many seconds it takes the parachute to open when you pull the cord. Because if you think, I have plenty of time, the higher you are when you start, the faster you're going as you get closer to the ground. And people who don't understand that don't get their parachute open in time. Oh no, I waited too long to pull the ripcord. That's why they tell you, watch that little thing. At least that's what people tell me. I'm not going skydiving. You go, why? Because I read once where somebody's parachute failed. Yeah, but that only happens once in a great while. Well, guess what? I'm not taking chances with a great while. And you go, but it's so thrilling. I'm thinking my life's pretty thrilling already. I don't need to step out of an airplane and take the risk of splatting on the ground just to have some kind of thrilling experience. 54. Some people need to go bass fishing. That'll give them a thrilling experience. 56. Now, see, every one of these, maybe you're saying, where's that formula come from? Don't worry about it. Somebody came up with the formula and it just works. So let's go to 56 and work that one. V sub n equals the square root of 3/2 times a. So, and here's what that means. When you're at an altitude of a feet above the earth, your view in miles extends as far as the circle called the horizon, and it's given by this formula. The greatest altitude reached in a manned balloon is 123,800 feet. So A is 123,800 feet. What was the view in miles from the balloon? 3 times that divided by 2 is the square root of 185700. That means the view was about 430 miles. If you got in a balloon and went up that high here in Kansas City, let me tell you, if there were no clouds in the sky, you could see Minneapolis, Minnesota, Chicago, Illinois, Texarkana, Arkansas, Wichita Falls, Texas, and Denver almost. And you could almost see Piedmont, South Dakota.
Where?
Piedmont, South Dakota.
No, wait.
Almost. If you were in Kansas City and you went up as high as this guy went, 123,800 feet up in the air. You better have on a breathing apparatus, because you're going to need it if you're up that high. And it didn't tell you to do this, but I thought, I got a map just to look at and see how far could I see if I went up in a balloon in Kansas City. Okay, enough of that. Let's move on to number 58. 58 says, find V if a body is dropped from a height of 45 meters. See that formula? If air resistance is neglected, the terminal velocity of a falling body in meters per second is given by this formula right here. And they're saying if a body is dropped, that means if it's dropped, there's no initial, the initial velocity is 0. You're just told here you drop it. If you throw it down, then the velocity has to be calculated into the formula. So you say, so what would 58 say? If it's dropped from 45 feet. So I take 45 meters, 45 meters times 20 is 900. The square root of 900 is 30. So he's going at 30 meters per second. That's how fast he's going when he hits the ground. Number 60 does the same thing again. Number 62. For 61 through 66, evaluate b squared minus 4ac. So they give me they give me a, b, and c. So I plug the numbers in. Something squared minus 4 times something, and that's all under a square root sign. And what goes here? B. So that would be 3. Change colors here. So I put a 3 here. What goes here? A. So I put a 1 here. What goes here? C. So I put a 2 here. Then I just do the math. 3 squared is 9 minus 4 times 1 times 2 minus 8. So the square root of 9 minus 8 is the square root of 1, which is just 1. All you do is just take this formula, plug in the numbers, and do the work. And stop when you get to 75, and let me show you how to work 67 through 75. See this little chart on page 310? See where it says natural numbers? Okay, just run across the list. Natural numbers are the numbers that we use to what? Count things. 1, 2, 3, 4, 5, 6, the way things naturally occur. So go across the list of numbers and put a little check mark in which numbers are natural numbers. Is 4.2? Do you count saying 4.2? I go 1, 2, 3, 4.4, 4.25. I count going 1, 2, 3, 4, 5. So which of those numbers are counting numbers. Which one is there's only one of them. Which one's, no, there's two of them, but one of them's a trick. Which one's the obvious counting number?
5.
5. So you put a check mark for 5. But what's the square root of 9?
3.
So where it says the square root of 9, take your pencil in your book and just put a little 3 there. Because the square root of 9 is a name for 3. So now that means 3 is also a counting number, isn't it? So you just go, you say natural numbers, you go across the row and put a check mark for the ones that are natural numbers. Then whole numbers. You know what whole numbers are? You don't know what whole. What?
Zeros, it's like the counting numbers plus 0.
There, it's the counting numbers plus 0. So you go across the column, across that row, and say, so where do you put a check mark? For whole numbers, you put a check mark at what? 0, 3, and 5. You follow me? You follow what's going on? Then go down to the next one. Integers. What are integers? The positive whole numbers, the negative whole numbers, and 0. So if you don't know that, write that in your notes. So then say, so which ones qualify for positive whole numbers, negative whole numbers, and 0? Well, there it is. 0. You understand what you're doing? You're just running across there and checking them all out. And then rational numbers. Maybe we should go to the next one. Irrational numbers. Which ones are irrational? You don't know.
Pi.
Pi is irrational. So you put for irrational, you put a check mark by pi. What else is irrational? All those radicals between the perfect squares. Remember? Those are all irrational. So then if you find the irrational numbers, which would be pi and the square root of 20 and the square root of 3, then what does that make all the rest of the numbers? Rational numbers. I'm helping you with your homework here. That's why I'm keeping you a little late, because I'm helping you do your homework. So the last one would be real numbers. Well, what kind of numbers would there be other than real numbers? Do any of you know of any numbers other than real numbers?
Imaginary numbers.
Imaginary numbers. Are any of these imaginary? Nope, they all look real to me. In other words, all the numbers you've ever worked with are real numbers. You haven't worked with imaginary numbers, have you? Have some of you worked with them? Was that fun, working with imaginary numbers? Some of you are going, what's an imaginary number? Okay, just for fun. Imagine the square root of -1. What number times itself would equal -1? There isn't one. But imagine if there was. Then we could have a whole new set of numbers to work with called imaginary numbers. That is really dumb math, isn't it? But it's so much fun when you get there. But most of you will never get there, and you're so thankful for it. Have a nice weekend, because I won't see you till Monday. And on Monday, we'll do the last topic in this chapter, topic 5.8. Then on Wednesday, we'll do the practice test. And then we'll have Good Friday and come back on Monday after Easter and take an exam.